Hi, this is Garrett Chenault and Robert Brand, and this is our final report for ECE 178. We controlled an LED color matrix that was using the FPGA Altera DE2 board. We used GPIO ports to communicate to the board. To start off, we're going to show the flowchart on how we actually implemented the code. So in the beginning, we initialize all of our values from our timers, all of our input outputs, and any other variables that we're going to need throughout the program. Then as you take the next step down in our flowchart, you have our return A, which we will explain later after we get to the bottom of the program. So what we initially do once we're done initializing is we write the switch values to their respective RGB values. This allows us to control the color for each channel. Then the next step of this is we set our clock high and clock low durations. What this does is it sends how long we want our clock to be high and how long we want our clock to be low as it is oscillating. The next portion is we check if the clock is still going through the high duration. If it's not 0, then we write a 1 keeping it high, and then we decrement the clock counter. We do that all the way until it is actually to 0. Then we know we're at the low section, so we write a 0 to the clock. Next, what we do is we check our row addressing. We have A, B, and C. A controls the finest adjustments of the rows. B checks twice as far of a jump, and C is twice B in the amounts of jumps. And it allows us to address each section of our LEDs. Finally, we repeat all the same steps for our clock when it is in the low position, and we return to A. So Robert will talk to us about how we implemented the system through Quartus and SOPC Builder.
Hi everybody, here we are in SOPC Builder, which is within Quartus, and these are all the components to our system. These first few ones are just kind of generic necessities. CPU, RAM, system clock, JTAG UART is to load the system and all the code onto the board. And then here we get down into 7 segments which aren't used, and then we have the 2 timers 0 and 1, which are going to be used for the delays in our code. And then here we have R1, R2, G1. These are all GPIO pins that are actually mapped on our board. We use this naming convention to kind of help us out later when we write the code, so we can address them specifically instead of saying GPIO 1, GPIO 0, etc. Here we also see the M_clock, which is a very important pin that controls a lot on the LED matrix. That pin is going to give us all the clock edges that essentially make the LEDs light up and align all the timing for our LED matrix. Next, here we have the system diagram in Quartus. This is just going to show like how we implemented the system, what pins we connected to what specifically on the board. This is where we show the outputs of our system. This is what pins or what systems we defined in SOPC Builder. This is where we're saying this is what you're hooked to physically on the board. So you can see where we have specific pin, like output port from ground, and it's mapped to a GPIO pin. This will be a pin physically on the board that we will connect to the LED matrix in order to get the value from our board, from our code, to the matrix. The system also had the ability to incorporate other features such as the hex display, which you can see there. But again, the important part were the output pins mapped to the GPIO pins, which is what we will be using. Here we have the Altera monitor program, and we're just going to show you how we load our system onto the board and what that entails. So we're just waiting for the system to compile onto the board. it's been successfully downloaded. Move the status out of the way. We'll compile our code. Code has been successfully compiled. Now it'll show up in the screen. We can kind of step through or run our program, whatever we decide to do. So here we just click run, and in the next section we'll show you how the LEDs light up.
So as the board is running, we're able to address the bottom rows. Here's R for red. And I'm going to turn that off and turn on green. And the next one will be blue. Now note on when we're capturing all of this on the video camera, the lights are extremely intense and the camera continues to try to adjust to find its equilibrium at white. So some of these colors will not actually show up at their true intensity or vibrance. So as we just showed, we can put an individual R, G, and B to either the top or the bottom rows. Now as we combine colors, we are taking advantage of additive color spacing. So blue plus green equals sort of a light blue kind of teal. Now as we throw R, G, and B all together, we will get white. So this is a very pure and intense white. As we turn off green, it gives us a vibrant violet. And when we combine red with green, we will get a yellow. So that's the next step. So we've got yellow on the bottom and a teal at the top. And we can control any colors we want. So as you can see, we were successful in interfacing with an ancillary device through the GPIO. This is an enjoyable project to work on, and I hope you enjoyed seeing it in practice. Thank you very much.